Good evening, everyone. Today is our second tutorial, and the recorded lectures will be on this YouTube channel. Let me share the link here. And the slides will be here. Maybe every link is different. Uh, okay, this is the link actually. Okay, let's get started now. So you have the YouTube link as well as the slides. Okay, very less number today. Okay, I'm Anirban Rai, PhD student at IIT Delhi. First topic is K nearest neighbor. It is one of the oldest machine learning technique developed in 1967 by Cover, Hodges, and Fix. Uh, so let's get back to our old example of that breast cancer detection, in which the zeros are like has does not have cancer and crosses are has cancer. So so uh, so suppose we are given a new point, suppose here, and you are asked whether this is a cancer case or a non-cancer case. Is it a cross or is it a zero? So how are you going to answer it? Uh, so uh, there is zeros and crosses, and you are given a new point here, and you are asked, is this a cross or is this a zero? So can someone say that? Say the answer. You can unmute today and tell the answer. What is this point? What can you say about this point? Is it a cross or is it a zero? Anybody willing to answer? Are you able to hear me first of all?
Yes, sir, but we can't able to see your screen, sir.
Acha, not able to see my screen. Is it small? Means
No, you are on meeting page. Now, yeah, now it is visible.
okay. So is this point cross or zero? What can you say about that?
Cross it is.
And how did you say that it is a cross?
Because the neighbors around that dot point are major are cross. That's why it belongs to cross data set.
Yes. So the concept of nearest k nearest neighbor is the same. The nearest neighbors are, and what the nearest neighbor are, that point will be the same. So suppose our k is here 3. So what we do here is we take the nearest 3 points. We take three nearest 3 points and ask each one of these, are you a cross or are you a zero? They all say I'm a cross, I'm a cross, I'm a cross. So 3. So it is definitely a cross. Suppose our point is now here. Okay. So the nearest may be this one. Okay. So cross cross 0. So 2 and 1. So most probably it is a cross. Okay. And maybe little far here, maybe little unsure in this case. Okay. But still cross. Okay. And now suppose here, suppose here. Okay. So given our k is 3, in this case 0 0 0, so it is 0. So this is the idea behind k nearest neighbor, and we are doing here a classification problem. It can also be used for regression. So like mathematically, suppose there is our test point x, and um, suppose there is a test point x, like that we have given the dot here, black dots, and given a set x that is of the nearest neighbor to x. So given a set x that is the nearest neighbor to x, and which is part of the bigger bigger set D, okay, set of points, such that the cardinality of Sx is perfectly k. Means cardinality means the number of points that are in Sx. Okay, so means what do I mean by this? There are k points that is nearest to x. Okay, and they are in the set Sx. There is also a bigger set D containing Sx. Okay. Now for all the x dash y dash, a new point that is within D but not in Sx. Okay. So what does it mean? Is that we have a point which is not nearest to x, but it is inside D. So k nearest neighbor says that distance between our test point x and x dash should be greater than maximum of the distance between. Sure. So if it is not nearest, if the x dash y dash are not nearest to x, it is not, that is x dash y dash is not part of Sx. then the distance between the test point and the x dash y dash should be more than maximum of the distance between a point that is nearest to x. Okay, is it clear? No. Oh. Is it clear? What does it mean? If x dash y dash is not nearest neighbor, then the distance between them should be greater than the distance with the nearest neighbor, maximum of the nearest neighbor. Okay, so this is the mathematical formulation of k nearest neighbor. Is it clear now? Hello.
Sir, one question. Every algorithm requires data set, right? So for example, KNN requires the data set during training phase. During inference, inference means what, sir? What does it
Inference
mean?
means like I have given this black dot. Yeah, is it a cross or zero? This question is inference. To infer whether this is cross or no, circle.
Inference means test data, is it?
Means finding out whether the test data is cross or zero, whether what is the value of that in regression, like that y value. So that is inference. Okay, we are trying to predict
Okay.
the test data. That is inference. Okay, so there are means there should be a metric to measure the distance. So that is called the Minkowski metric, defined like this. For every component of the 2 points, the difference between them raised to the power p, and the summation is raised to the power 1 by p. Okay, and if p is equals to 1, then it is the Manhattan distance. Okay, mod of these two, summation of these and to the power 1 by p. P equals to 2, then our popular Euclidean distance, and if p equals to infinity, then we will get the max distance. What do I mean by this is, if it is a very large number p, okay, so what happens is, suppose the one difference is 30, sorry, another is 15, another is 7, okay, and if raised to the power infinity, what will happen is that only the this one will be a this one will be so big, then this, if these are raised to the power infinity, they are almost negligible. Okay, so this can be ignored, other components can be ignored. Okay, and now this will become according to the maximum difference. Okay, so this is called max distance. Okay, so here is your question. Before the during our start, we have discovered a classification problem with it, but now this our problem is a regression problem. So, so as you can see, these are the three type of distances. So here we need to use the Euclidean distance, and so you can see that you have to use one.
Sir,
Okay.
sir, can you please repeat that p equal to infinity?
So means you can see that means means like suppose there are points. Okay, 2 points at least are needed. Okay, So, and suppose there are three components for it, three dimensions. Okay, so suppose the difference in the x component is the maximum one. Any component can be maximum. Suppose it is in the x direction, then raised to the power infinity, others will be almost negligible. Okay, compared to this one, because the power is so large here. Okay, so
Okay, sir.
only the maximum one will dominate. Okay, others are not.
So there X and Z are matrices.
And now x and z are components. Okay, suppose this is 2, 3, 4. This is 5, 6, 7. So it is like 5 minus 2. 5 is x and z is 2. Okay, so it is 3. And suppose the power is 2 here. 2. Okay, summation over the dimension. Okay, 6 minus 3, 3. Power is 2. Then 7 minus 4, 3. Power is 2. 4 raised to the power 1 by 2.
Okay, sir.
Like that. So here as well, as you can see, so what we're going to do here, so everyone try this. What is the idea here? Can anybody unmute and tell? You have to use the
First, we have to calculate the shortest distances between the points,
hmm. Now
and then we have to identify.
how are you going to do that?
Now the first point is, let's say x1 is minus 1.0, and x2 is minus zero point 0.05. Then the distance will be square root of x2 minus x1 square plus y2 minus y1 square.
Uh, y2 y1 where are you getting from? See, means like in each component there will be subtraction. So for first one it will be minus 1 minus 0.5. Okay, okay, and square of that, then plus minus 0.5. Acha, y2 minus, yes, maybe you have said that x2 to be y2 minus plus 1. Okay, it will be plus now because minus minus plus, and square of this, then square root. Like that you have to calculate rest of the 3, 4, 5, 5 distances. So the can you try now?
Sir,
Yes.
so why can't we use mod of Manhattan distance to calculate in such questions?
Or you can use any actually. This what I have explained here is like these three are the most common ones. You can use any p value, p 0.5, p 1.5, p 1.67, anything would
Okay,
work.
sir.
But here it is written that you need to use that. Okay.
So Manhattan and Euclidean distance would give the same result, right?
No, means like the answers means our inference will be same, but the
No, not the
y value
distance
will be different.
exactly, not the distance, but
Hello, what you say?
so not the distance. Like Euclidean and Manhattan distance obviously cannot be same, but the answer, the three nearest neighbors will be same.
Yes, yes, absolutely. Inference will be same only.
Okay, sir.
You can use any value. So calculate and tell me which are the three shortest, three nearest ones. Which points?
3 nearest are 1.5. First we will get minus 1 0 minus 0.5. That is
Minus.
first one.
Huh? First one.
And second one.
Acha, acha, okay. And
First one, second one, and last one.
yes, correct. So that is it. And the these are the nearest one. So for means to use as a regression, what you have to do is take mean of these three. Okay. So first one is means minus 1.947 and minus 0.391 and minus 3.451 divided by 3. So that is the answer. Okay. So how do you did you understand how to do KNN regression now? Because we've started with the classification. Now we have understood regression as well. The only difference is taking the y values and taking the mean of those mean of the nearest ones.
Sir, what will happen if you take k value as a, like now it is 3, if you take more, then what will happen?
Uh, More means like you to consider different points, more points to get to the inference actually. So what happens is if the k values is less, so it overfits actually, and if the k value is more, then it has high bias. Means okay. Let me explain this one. I think the next one is only that. Okay. So like these 2 points, a linear regressor requires training points during inference. Is it true or not? So, so what do you say here? First is true or not?
Yes, sir. First and second are true because every for all the algorithms, training dataset is required only.
No, no. First is not actually. During inference, I already have my hypothesis ready. Suppose my hypothesis will become as the example I've given in previous day. It is already ready. Okay. So after this is ready, for making inference, we only need the test data set. Okay, that is x1, x2. If x1, x2 is given to me after training, then I don't need the training points. Just put x1, x2. Okay, and you'll get the answer. So training points are not required during inference in linear regressor. Okay, but uh, during the KNN regressor, as you can see that we were using the y values of these points, okay, to get to the y value of our own point, okay, or test point. So the training values are required here. So the next one is like as you are taking into consideration more points, okay, so it does not overfit actually, okay. And if like if you're taking like small points, let's go to our previous example. uh, Suppose here is the point the k equals to 1. Okay, let's delete some of this. 220. Okay, yes. So k is equals to 1 and our point is here. Okay, so I want to know whether this is a uh, x or o. So as I'm taking k equals to 1, so this is the nearest point, so it should be x, right? But what happens is after training, uh, it can happen that uh, means like suppose uh, means like suppose in situation like this, this point is there. What do you say? It is X or O? Okay, it can be very much likely that it can be O as well. Suppose it is closer to X. Okay, but it can be very much likely that it can be O as well. Maybe little distant. So in that case, it is not a good predictor. It overfits. Okay, so taking consideration of many points is a better idea. So so this is the answer. If higher value of K is there, then less prone to overfitting. A linear regression partitions the space into multiple regions such that the prediction over is a given region is constant. So that is not true. Linear regression is along a line. It fits a line, and the line predicts the value. Okay, and so this is like the classification one. It means it puts a line. Okay, and the region on one side has all the same classes. So it is what it is saying is classifier, but the thing is it is called as a regressor. So it is not true. Okay. Okay. So another KNN classifier one now. Okay. So you can do this. What should be the idea? Can we tell?
Same way we have to calculate, and finally we have to take majority here.
Yes. Yes. Whichever has the highest which class has the highest vote will win here. Okay. Can be done? Any doubt? Anybody has any doubt?
Hello.
Hmm.
Sir, can you please explain that question number 9?
Question number 9. This one, huh?
Yes, sir.
This one I will reach. Okay. This is part of the regression. Okay, a lot of derivation and stuff there. Okay. Not now. Do not understand now. Okay. So first is now. Any doubt in KNN? KNN is done now. Okay. Now bias and variance will start. Any doubt in KNN? Okay. So bias and variance. So bias and variance are very important machine learning concept, which tells us whether a curve that we have fit is perfect or not. Means that it helps us to get to the best possible curve for our prediction. So, if you can see the example here, this are you able to see the dots as well? This is small for sure.
Yes, sir.
Okay. So quite a zigzag dots here. Okay, like that. Hmm. So so as I'm the question creator, I know that this pink one is the best fit. Okay. Okay. So, but if you focus on the blue one here, okay. So what happens is that it is a very simple curve, straight line only. And as I said, the pink one is the better one, but straight line is like a simpler one. Just say key like काम चल रहा है type. Okay. So you can understand that this blue line is blue straight line is not trying to learn the data. Okay, it is like it is biased to be a straight line. Okay, it is biased to be a straight line. It is not trying to account for the properties of the data. Okay, so I say that this blue line has high bias. Okay, and and what will happen to that is that the error on the training data, okay, error is these distances, error are these distances on the line. Okay, error are these distances. Something happened. Okay, so this error will be high on the straight line. Okay, error will be less in the curved line, and error will be, as you can see, that this yellow line is perfect, is perfectly fitting the data set, so the error will be 0 on the yellow line. So okay, okay, so as the error will be 0 on the yellow line, so it has zero bias. It is not biased by any preconception. It is just trying to perfectly fit the data. Okay, okay, so this yellow line has zero bias, this blue line has highest bias, and the red one has in the middle. Okay, and so what you can see here, I have copied and pasted this one here. Okay, so and this green ones, green crosses are our test data. Okay, so you can see that the yellow line performs very poorly on the test data. Okay, because it has high means it is perfectly fitting the training data, but it is so complicated that it is not able to predict on the test data. Okay, has high error on the test data.
Sir,
Yes.
so yellow line has high bias as well, right?
uh Not high bias. Bias is like the yellow line means that here the blue line has the highest bias. Okay, red in middle and yellow
Bias
the
is
least.
like getting biased by the test points.
No, no, no. Bias means like that is biased towards a straight line. Okay, I want a straight line, but this converter is not able to fit the data. Okay, so it is to my own bias that it engages with the regression, but it is not working. Okay, that is called
Okay, sir.
bias. Okay, my own bias. Bias means like my preconception. Suppose I am biased towards one student and not another. What does it mean? Like I have preconceived notion about a student. Okay, that suppose he is a bad student and I'm not teaching him properly. Okay, so it is unable to fit the information into his head properly. Okay, so I'm performing bad due to my bias towards him. Okay, as I have not seen the training data, but I am already making assumptions on the training data that it has to be a straight line like that. It is called bias. It is bias on the trainer. Okay.
Sir, is it bias? Is it a error? Predicted minus actual?
Uh, yes, but we will not go into the detail for now into bias and variance. I will get into it the next time. Only the introduction is enough for now. Mathematics I will get in next time. Okay. So what happens is that variance is the uh, means the difference in the manner how the curve is able to fit the training compared to the test data. So you can see the yellow is very much perfectly able to fit the test training data, but yellow line is not at all able to fit the test data and make good predictions over it. So yellow line has high variance. Okay. and uh, and uh, and you can see that um, means the other two have low variance. In the case that pink line has the least variance. Okay. And blue line is the middle one. Okay.
Sir, always is it high bias means underfit the training or how it is, sir?
Yes, high bias always means underfitting. Okay. And high variance is overfitting the training data. Okay. So what happens that both blue and yellow are unable to be a good predictor. Okay. Unable to generalize better. Okay. One is underfitting, one is overfitting. So we will use this bias and variance information to get to the pink line, that is the just right fit one. Okay. Okay. So that is the idea. So what methods do we use to get to the best fit? First is regularization, another boosting, another bagging. So these are the three methods used to get to the perfect fit, considering the information provided by bias and variance. Okay, that is the thing for now. Okay, so here is our question. So what do you understand by this? First of all, that first one has to be a linear, right? A suppose, but you have to understand that here it is a plane actually. Okay, it's like it is a 3D diagram, and first one can only be a plane. A is in our case it was like 2D diagram, so it has to be a line, but here it will be a plane. And this one, as there is x1 x2 combination, okay, so you can understand that it will be a curve, means like uh, how do I say, a surface like that is not plane like that. So it is like a more complicated one. Okay, like in our yellow case is the more complicated one. Here the is anything that is a more complicated hypothesis is a is like the any
So the first question is a plane.
first one is a plane. Yes.
So then what is the second one? Like what does it represent geometrically?
It is a surface. I don't know, just more complicated surface.
Okay.
So as the second one is more complicated, so on a given training data set, the mean squared error of I is always greater than equals to 2. That is correct, right? Because as you saw in the complicated one, the training error is least. Okay, so So 1 should be greater, right? Answer. 1 is likely to have higher variance than 2. Wrong. Okay. 2 is likely to have higher variance than 1. Right. If 2 overfits the data, so it is given that 2 overfits the data, then 1 will definitely overfit. That's wrong. If 2 underfits the data, okay, then 1 will definitely underfit. That is correct. Okay. Because you have to understand that second one is more likely to overfit. Okay. But in this case it is underfitting, then the one that is simpler should surely underfit, right? So that is how it is done. Okay, any doubt?
Yes, sir.
Okay.
Sir, in this question, the last point which you have mentioned, it is correct. I feel like that this point means that it might have more flexible form than capture the data better, I guess. So it is incorrect as per me.
How? Repeat, please.
Yeah, this point is incorrect as per my understanding
Last one.
that if second underfits the data,
Hmm.
it does not imply that first will definitely underfit. It might have more flexibility form that it captures the data better.
No. You have to understand that as the first one has more bias, it is less flexible actually. This one is more flexible. You can change you have another beta 3 parameter here which you can change to get new shapes. Okay. Here the beta 3, first one, beta 3 is always 0. Okay. So it is biased towards making the beta 3 0. Okay. So second one has more flexibility
Okay, sir.
in changing that beta 3 and getting different shapes. Okay. These parameters are the one that we are supposed to estimate. Okay. So in first one the beta 3 is always 0. So it is biased towards beta 3 being 0. Second one, beta 3 can be changed. It is flexible on beta 3. Okay.
Okay, sir.
Any doubt? Bias variance. Any doubt? So we move to the next part, that is hmm, hmm. So we'll get to the mathematics on regression now. So as you can understand that in any experiment, when you're collecting data, uh, for any inputs that the output that we are getting from the experiment will have always some noise due to the measurement error that we might have done, or human error, device that has error. Okay, device is not perfect. Okay, so due to that we might have some noise, that is called noise to the data. Okay, means that okay, so what it means is that the data is not perfect. Okay, like you have done experiments with different instruments that it might not the instrument might not be on 0. The instrument may have means there can be error while reading the instrument. Okay, instrument might not give the right reading. Okay, so for that we have some error in taking the data. Okay, so that error is called noise. Okay, So here, like, so here we have the data set xi, and ti is the noisy output for every xi we have, and there are n training data set, n training examples. Okay. Our purpose is to learn why here. Okay. And so why is the values for x which has which does not have the noise. T that we have taken has noise. Okay. So what we define it like that noise can be added to our uh, perfect data. Means we do not have a perfect data. T is the thing we have. So T is defined as like we are like adding some noise to the perfect data that is uh, that that we tried to that we tried to gain through our experiment. Okay. Why is the one we need? We have got T, and so this is the relation, and here this E eta is called the noise, and it is defined as the Gaussian distribution with zero mean. And that in do you know about Gaussian distribution? Gaussian distribution, normal distribution. Hello. Gaussian distribution, normal distribution. Any idea?
Yes, sir. We know about normal distribution.
Yes. Gaussian and normal are same. I don't think everybody will have idea. So here it is. Okay. Where do I start? So this is a slide from somewhere. Okay. Satish Kumar. So prior, prior and likelihood. Prior.
No, sir.
So let's understand. So first let's start from here. Okay. Bayes theorem,
Yes, sir.
Hmm. So Bayes theorem is like this. This form you have read, I think. So this CK class of means probability of this class given this training example. Okay. It is like this PCK probability of occurrence of this class. I already know. Okay. So this is called the prior. Okay, maybe it is not required for now. Okay, let's go to the Gaussian one. So this is the form of the Gaussian distribution, which denotes that this xi values means I have multiple xi values. Okay, so they are distributed according to the equation this. Okay, so what does it mean? Okay, let's have this. Let's have this one. So you have this equation. What does it denote? That here the xi bar is like the mean of the data. Means you have given a data set that is like different x1 xi values. Uh, hmm, okay, so different x1 values. Suppose 1, 2, 1, 3, 5, minus 1, 4, 9, 6, 9, like that. Okay, can be anything. Okay, so the mean of the data is this. Okay, and variance is this is sigma is the standard deviation. Okay, the standard deviation, you know. Okay, so mean and standard deviation, you know. Okay, and standard deviation square is variance. Okay, so uh, what do I mean by Gaussian distribution? Is this bell-shaped curve? What does it mean? Like, given this is 0, okay, origin, given a x1 value, xi value that is on the x-axis, this value, what will be the uh, this? Okay, this is like a probability distribution. Okay, probability distribution, given the x value, what will be the probability density, probability density function. Okay, this probability density function, what will be this value? Okay, so this is like this curve. Okay, bell-shaped curve. So highest probability density is here. Okay, okay, so what does it mean in our case? So as I said, this quantity noise is distributed um, as a Gaussian distribution with zero mean. So that is our xi is 0. Okay, yes. So xi is 0. Where did I go? Maybe here I've done mistake. No, I don't know where. Okay, so there is our xi is our xi bar is 0. Okay, and that beta inverse is called precision. Okay, yes, beta inverse is called precision. What does it mean? Beta is equals to 1 by sigma square. Okay, so in not writing in terms of sigma, I am writing in terms of beta. Okay, so this is the thing. Okay,
So beta inverse is sigma square. Okay.
and what does it mean actually? So it means that given the points, they are more likely to be distributed around the mean 0, and as we move forward, that means towards the infinity, positive infinity, points become less and less. Okay, so you understand, right? Means the frequency of points is more as they're close to 0. Points who are close to 0 will have more frequency, and as it becomes more negative, less and less, as it becomes less, more positive, less numbers of that. Okay, so that is the idea behind this distribution.
So can you tell why the noise follows the normal distribution only?
It is an means approximation, because the linears are habituated towards normal distribution, and most of the real world data follow normal distribution. That is the main reason. Okay, because it is a good approach, because most of the uh, uh, string data, any type of calculation, any type of data that we have follows a normal distribution. Okay,
Okay, sir.
special cases it may not be, then every then this derivation will become difficult.
Okay, sir.
For now, like this. And in the previous class that you have seen that this y is that is the hypothesis here. Okay, is the linear combination of this is the weights or the parameters and the basis function. This phi of x can be like uh, any type of function. Okay, suppose like, so this is w1 x square, x1 square, and then w2 x1 x2 square, this is x1, this is w3 sine x1 x2, any type of function. Okay, linear combination of that. Okay, so what does it mean? But any type of product between parameters, and there is a weights and basis function, and sum of these, that becomes the linear combination. Okay,
So basis function is like the x or the features which span the entire space in which y lies.
yes.
Okay, sir. So those basis functions might exist. Like how do they exist? Like x1 and x2 are separate basis functions, or do we consider x1 square as one basis function, x1 x2 square is
X1 square
another
is
basis
a
function?
separate basis function, x1 and x2 square is separate basis function.
Okay, sir.
So moving on. So we need to understand what is likelihood. Okay. So so okay. Let's see. So as you can see, uh, likelihood is the joint probability of uh, xk here is what? Okay. Okay. So it is the here dk means the t that we have considered. Okay. I think so. And this and our x. Okay, so product over all the training examples. Okay, so that is the likelihood or joint probability. So
Sir, can you please explain the concept with an examples?
wait. Okay, so likelihood is, as you can see, is that probability of occurrence of one training example. Okay, this is x and this is y. Okay, probability of occurrence of one training example and multiplication of all these. Okay, so you have to understand is that here the uh, training examples are IITs. Okay, so what does IIT means? Uh, 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 Independent and identically distributed. What does it mean? That so this likelihood is the probability of occurrence of the data. Okay, okay, and so as by the rule of probability, if the data is independent, each training example is here independent. Okay, so what does it mean? That you can separately multiply the probability of each. So that is product over q multiplication of each probability because they are independent. Okay, and so independent and identically distributed. So they follow a fixed distribution. Okay, so that will be normal distribution in our case because it is the most common distribution. Okay, so this product is because these are independent data sets. Okay, data training example and and okay, so that is it. Okay, let's see.
Sir, varying the values of k generates the different test the data points, right?
Anyway,
Like the
likelihood
this
of
ordered pair x.
likelihood will not generate them. It's like you have to understand that we get the training examples. Suppose we get the training example from an experiment. That is, we are doing experiment for x values. We are finding some y values through some instruments or something. Okay, but in some coding problems are given. Suppose yeah, they do not give the training data. They just say that here are the x values. Uh, no, so not here, not even the x values are given. You are given this distribution, normal distribution, or can be any distribution. Okay, generate training data from this. Okay, so uh, what we have to do is that you have to use the randomly you have to generate data from this using Python. X values will be you will be able to generate. Okay, and suppose some expression is given. Some expression suppose can be complicated, but uh, x square plus x. Okay, like this. So you can get the y values as well corresponding. Okay, but this is like some problems are given like that. But you will get means the practically the xy values are always from an experiment. Okay, okay, so as you can understand that as so here this w transpose x, this y is distribution, we consider this y is distributed normally, that is in the y values are in Gaussian distribution. Okay, and this noise is also Gaussian distribution. Sum of two Gaussian is Gaussian. Okay, and okay, no, sorry, got it wrong. Why? Yes, actually correct. Okay. So this y is normal distributed, and this noise is also normal distributed, and so we get the normal distribution having this what is it called, precision beta inverse mean w transpose phi x1, and it is over this ti examples. Okay. Okay, the variable here is ti. So as you can see here, here the variable was xi. Okay, so that is how we got the normal distribution, and given the expression of likelihood, it will be overall training examples n.
So Ti is the predicted point.
Yes, in the training example that we have, that noisy data, noisy y is the one. So from experiment, the value that we have got is the t. Okay.
Okay, sir. So, sir, the expected values of like not the expected values, the predicted values are do also follow the normal distribution.
Yes. Okay.
Okay, sir.
Okay. We'll start from here after 10 minutes. Okay. A break. If we get the dinner. Okay. Then let's start again. So the next part will be maximum likelihood estimation. So we would maximize the yeah, means maximize the likelihood to get the parameter w here. Okay, so that will be our work. Okay.
हेलो एवरीवन, क्या मेरे को कोई सुन पा रहा है?
Yes.
Yes.
मैं ये पूछना चाहता हूँ कि जो रिकॉर्डेड सेशंस में सर जो मैथ्स पढ़ाते हैं, मतलब जो मैथ्स भी होता है उसमें, वो आप सबको बहुत अच्छे से समझ में आ जाता है?
No, not at all. Not at all.
तो वो
This
मैथ्स
is my thing that I am really not okay with those explanations.
That's what I told to explain with an example because it is very difficult to understand with the expressions.
yeah, it is difficult to understand the expressions, as well as we are not able to relate that how is it applicable to real world data.
Correct.
Actually, right. Right.
So unless and until we are more likely to understand the mathematical expectations and how the functions behave, we won't be able to put them or like apply to real world data, right?
Yeah.
Yeah, totally agree to that. And even the people, those who are really new to this concept, like if I take my own example, I am really struggling in understanding the very simple equation also. So I have to go through another links as well to understand the very basic knowledge about them.
Yeah, yeah. Like I am also an engineering student. I am able to grasp a few concepts, like most of the concepts, but there are so many like points in the lectures, in the recorded lectures, they are really very, they have soft corners, and I'm not able to get those. And how is it like if we ask to Sir Anirban Ray, sir? Hello.
And one problem which I faced is the assignments will be different and the content which will be recorded that will be different.
Yeah, definitely. That's that's not a very big issue, but like, do you guys follow some other YouTube sources or somewhere other sources to get familiar to those mathematical equations?
Actually, I am following few, but they are not specific. For example, if I am not getting what is regression and this linear regression, so I am going through various links on YouTube just to understand the basic knowledge, and then I am solving the question. And today also, when I was solving my assignment, it took around half an hour to crack one question, just one question to crack the fifth one, question number 5, because I really don't know. And when I go through those links and the recorded lectures, there I have also gone through the whole lecture, but no, not at all. I'm not able to understand, relate that what they are saying, what the question is asking. And again, the links which I am following on YouTube, they are also like they're explaining in their own pace, so there is no relativity which I am uh, having right now.
Yeah, I totally agree with that. Like, I'm also not able to find some viable resources for the maths part, especially.
There will be not. You will not be able to find. The reason being because YouTube is providing only those topics as a very in a very basic mode.
Yeah,
They are just giving you the whole soul, the basic understanding about that thing. But when we are solving the assignments are totally somewhat based on some data set and all. So data set is not available on Google. You need to put your own knowledge and understanding after going through those links. So it's taking a lot of time.
yeah. Like what I feel is what we are needed to work on the data sets that are being provided in the assignments is just like similar to in Python, as we from the SciPy or the scikit-learn module, we import the linear regression. So we are just importing the linear regression, and all the fit and transform, all that stuff is being done by the backend or whatever the Python code it has already been written. But all those things, how they are actually working, are being taught to us. Like, what is the basic maths? behind, or differentiating the vectors part to get the actual equations and how to minimize the errors, all those sort of things. So
Hmm.
that's
Right.
the basic idea behind the assignments. And I guess that's actually working because like if we have to go on a higher level, we have to understand how the data would behave in certain situations. We have to anticipate. So
Right.
knowing that knowledge, basically the foundation is maths. So without understanding maths, I don't think we will be able to get through a very that point where we actually know something and we have can pride of it.
Right. Right. Can anyone tell me that where is the sir right now?
He said he'll be taking a break of 10 minutes. So probably
Okay.
that after that might be returning back.
Okay. Okay. Thank you.
Yeah.
Hello everyone, I'm back. So let's get started. Some doubts here. Yes, I will share the presentation. No problem. So, we need to uh, maximize the likelihood. So, what does it mean? So, likelihood is this, okay? Maximizing the likelihood means that we are trying to maximize the occurrence of Ti for some values of x, okay? Okay. Uh, for that, we in such values of w that that this probability is maximized, okay? So for that, what we do is whenever for that we need to take derivative with respect to w. Okay, let's see. Maybe I have not done maybe theta here. Okay, let's see. Some parameter theta for which the likelihood is maximized. Okay, and that theta is what we need to find. Okay, so what is that? Arg max with respect to theta. Theta is w and beta. Okay, these are the two parameters we have with respect to which I need to maximize the likelihood. Unable to understand. Actually, I don't have the writing pad. That is why it is bad. So arg max, okay? Argument max, okay? So the argument is important, okay? Theta, the theta we need to find, okay? And of what we need to maximize likelihood, okay?
So, can you explain what is likelihood, like on a in simpler words, apart from mathematical equations?
It is a mathematical concept. So
What
likelihood
does
is
it signify basically?
okay. So it signifies the occurrence of Ti here, okay? Given this parameters w and beta, okay? The occurrence is I'm trying to maximize. Okay, let's try to understand it this way. Okay, someone joining. Numbers reduced drastically. Okay, so let's try to understand it this way. So I have the points as you know, and I need to fit a curve. Okay, so what I'm saying is I am trying to best possible predict Ti, maximize the occurrence of Ti. What does it mean is that I'm trying to reduce the error with respect to the curve I'm trying to fit. Okay, I'm trying to get close to each Ti, okay, as much as possible. Given these parameters x, phi xi, given the variable phi xi I have. If it is more complicated, I have more ease of going to the TIs. Okay, so means more like
TI The points on the line.
Hello, what you saying?
Ti are the points on the line.
Yes, absolutely. Okay, so I'm trying to get to this point. Okay, given constraints are this expression of phi x. Okay, so I'm trying to get to close of this uh, points. Okay, and at this is represented by the likelihood. Likelihood is maximized given the phi x, then I will be as close as possible. Means reducing the error as much as possible. Okay, so and you can see here this x I have already defined. Phi x I have defined myself. Okay, where is it? So phi x I have already defined myself. Suppose this one. Okay, so but the other parameters are w and you have to understand w is here a vector. Okay, and beta is a scalar. Okay, w is the vector representing the dimension of phi x. Okay, and beta is scalar. These are the two parameters I have, and using which I can maximize the likelihood, which means that I'm taking the curve in such a way that I'm most likely to occur at the our given points. Okay, so that is likelihood, most likely to occur at this point. Okay, as much as possible. The constraint is this phi x. Okay, so here we are. So um, whenever we are taking derivative, we take the log of it because log is the increasing function, so it does not change the critical points. Okay, and we take negative of that because we always like to minimize. Okay, so you may not take the negative one, but log is important because it takes makes the derivative uh, easier. Okay, so this is how it is. Usually um, take the negative. Okay, if I have written it correctly. Okay, so this is the normal distribution. Expression is here. Okay, so sigma I square will be like beta I under root beta I by 2 pi. Okay, so under root gets half here. Okay, and beta. Okay, let's do away with the negative. Maybe what I've done I don't know now. Okay, so this is positive and this should be negative, and this is negative. Okay, maybe I've done it positive way only. So let's change this one. So this is plus and this is R max. Okay, max. I hope you're able to understand. This will be plus. Okay, so to understand here that this first term will become beta I square by 2 pi. Okay, because I'm not taking beta I by 2 pi under root whole under root. Okay, so under root of beta becomes half comes forward to the square root and log beta, and negative of half log 2 pi. Okay, this half is from the square root. Okay, logarithm of that, and exponential and log over exponential both cancels each other out, and we are left with this one minus beta by 2. Okay, everything is clear up to now. We have not done any derivative one, partial derivative we have not taken, just simplifying the expression, taking logarithm. Okay,
Sir, it is very difficult to understand. Please take up examples and explain, sir.
Which part means of my handwriting or what?
Yeah, understanding concepts, sir, this maximum likelihood.
Sir, actually, whatever you are taking as right here, they are very good. Okay, fine. But when we are not able to connect with a real life example, that where we supposed to use it.
No,
I mean, if you will take a very
as I
simple
explained here,
example.
as I explained here, na, this I'm trying to make a curve such that the error is minimum. Error is minimum means that I'm trying to, as much as possible, trying to predict the TIs. Okay, means taking the curve like this as much as possible. This is the best possible. Overfit it, I know, but this is the best possible curve. So what does it mean? And this curve is represented mathematically by the likelihood here. So I'm trying to maximize the likelihood. What does it mean? I'm trying to take the curve to every point and fit them as perfectly as possible. Okay, so this is what is likelihood. Nothing more than that. Anything more you do not understand? I know this is hard because probability I think you not have studied well. Okay, so just taking log and separating these. Okay, any other doubt? Or are you able to understand? Okay, so as you can see here, the beta terms are this first term and third term, right? So I'm separating these and differentiating with respect to beta. Okay, okay, so beta, this term is coefficient of the beta like that. So taking derivative, beta will go away, and here this is log, so 1 by beta, so 1 by beta, n by 2 beta goes to 0. So I have the expression which I have the value of the noise. Okay, for which means the variance in the noise. Okay, beta is here, variance of the noise. Okay, so this variance of noise is this one. Okay, so but this part has not much significance because the variance of the noise is experimental and we can do nothing about it. Okay, we that is what we have occurred in the data, but it can happen that means okay, so let me explain this one. This is the precision of the noise. Okay, but the most important thing here that we need to find is the W. Okay, so this W's are the parameters that we need to find, the parameters of the curve. Okay, derivations are important to understand but not to memorize. And the last question will just occur at that answer the last question. Okay, this is the answer of the last question. Okay, from this derivation. Okay, so we are now here. So the W terms is only this one, last one. Okay. So we need to take derivative with respect to W and put that to 0. Okay. And you must have remembered that in the previous class, they are also for solving that question number 5, I took derivative with respect to W here. Okay. And this was the expression. Whatever that was with W comes here. Okay. And that equate that to 0. Okay. Now what do I do is like separate this these two, summation over n, separate these two. Okay. So how much we are able to get there? Some doubts here, I think. Can you suggest any book that has ML mathematics? Yes, I would like to suggest. This is the best book there is for machine learning. Bishop, pattern recognition, and machine learning. It is free from Microsoft here. Bishop, pattern. The writer of the books works at Microsoft as and has made it publicly available. All very big scientists here, pioneers of machine learning, Sholkov, Jordan. Okay, it's the best book, but very hard book. Okay, not easy actually. I will actually maybe I will find it here also. Give some examples from here. Means you need to understand the probability part better actually. Then it will become easier. Probability parts also explained quite well here. Okay, this Gaussian distributions. Okay, at least you can read the first chapter. Okay, will be nice. So our exercise that we are doing is on page 27, as you can see here. Lot of illustrations are given actually, maybe easier to understand. Okay, you can refer here. Page number, or better to read the first chapter only. Okay, is this introduction from here? Probability, everything well explained. Probability is very hard to cover actually in machine learning class. It is important to have the prior knowledge. Probability. Okay. What we are doing it is in chapter 27, means page 27. Okay. PDF link. Okay. Okay, I can give the PDF actually. Is it possible? Let's see. Okay, let's move on. Here it is. So, so here try to understand. Actually, there is quite to understand here. So, so
Sir,
in
sir, can you please solve through numericals? It will be more easy to understand this concept then.
numericals will not go through this step. Actually, we'll just use results of this derivation. As you can see, this one. Okay, only use the result of this derivation. Actually, yeah, previous class actually I did use a numerical question number 5 to solve this one. Question number 5, you'll remember that I had done from this step. Okay, we had the square error function. Okay, which is literally this. Okay, beta is not, as I said, not that important. Okay, oh my god, beta is not that important. Okay, important is w here. So we had the square error function. We took derivative of this. Okay, and there were three expressions formed. One with 1, another is x1, another with x2. I already have that one, so let me show you. So these were the three expressions. Okay, so cool thing is that uh, you can write, you can understand that here this hx minus y that I have is common in all three, and m is not important. Okay, hx minus y is common in all three. So I had used example, but not gone to the rigor of the mathematics there. Just I had used the squared error. Why do I need to use the squared error? I have not explained previously. So you can see that from the expression of likelihood, taking log of that, we get to the squared error function. Okay. So the squared error function is and is dependent on the consideration that our distribution is normal. Okay, the data is normally distributed. Okay, from that we get the squared error function, squared error expression. Okay, so what is explaining is this one. So as this is common and so this can be written as a vector here. So this part is multiplying to all three. Okay, and this is equals to 0. That is I need to explain here is this phi x is actually a vector. Okay, vector of the vector of this, vector of this, this, then after this, then after this. So vector of these three. Okay, and this is our old expression. This is a scalar. Okay, Ti is a scalar and W transpose phi is also a scalar. Okay, clear up to this? So we separate these both out. Ti into vector of phi that I have, so scalar multiplied vector, and W transpose phi is a scalar, so this is, and this is vector. So but separately this is vector, this is vector, and this is W transpose is the transpose of the vector. Okay, so clear up to this? Clear? Any doubt? Maybe chat doubt. Thank you. W is the weight matrix. Yes. No, no, not weight matrix, ma'am. Weight vector actually. Means W is this W1, W2, W3 like that. Okay. Can be bias term as well. Can there can be a bias term as well. In bias term, we consider the phi x to be 1. Okay, like that. I've explained previous class that one. So I separate this one, okay, and now it is the important step. So this is the summation over all training examples I, as I've written here. So what does it mean that I have n such equations? Okay, n such equations, and this is very computationally expensive for a computer. Okay, for humans as well. Suppose that there are n equations we need to solve. Okay, like in our case there were three equations. Okay, no, not three equations. So the so you can understand this was the condensed equations that I had formed. Okay, not three, means like this became one. Okay, in vector form, but means there were some training examples here as well. Training, yes, this is the one, right? How did it become big now? Oh, shit. Okay, and these were the this six training examples which will fit this. So there was six expressions. Okay, this is the one. Yes. No, what was that? Okay, I have this one. Actually, summation is there, no? Summation. Yes. Summation over those actually. Yes. Means not n equations here, just a summation over those, but still completely computationally expensive. So not six equation, only one equation, not n equation, only one equation. But means the summations are required. Summation over I, as you see. Okay, and so what we do here is that we try to um, vectorize here. Means like we have to remove the summation. Okay, so you can understand from here is that this ti scalar multiplied phi I vector. Okay, so I now have made phi transpose as a, means phi as a matrix now, and now t is a vector. So you have to understand t is like all the values that I had, 1 2, is all the y values that I had. Okay, they have been formed into a vector. Okay, t, and this phi transpose is like, let's see, how do I define this? Let's see, this is this vector. Hmm, hmm. Okay, let's understand from here. So I need to multiply this vector t with a matrix such that we, means for each value of this t, means suppose for 1 I should get this expression, right? So uh, so this has to be like how to explain, means suppose the, let's simplify the phi for once. Let's not use this one. Okay, very complicated, very hard to write. Okay, uh, let's use this one. Okay, 1 phi is 1 x1 and then x2. Okay, so this will become, for first training example it will be 1, and then x1 will be whatever x1 it is. Okay, so x1, And for first training example, I use one superscript. Okay, this is x2. And for first, I use one. Okay, and then there will be second one. So say 2 here. Okay, and like dot 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 dot. Okay, like that. This is the transpose of this. Okay, so this is phi transpose. Okay, this is phi transpose, and so phi is like 1 x1 1 x2 1 1 x1 2 x2 2 dot 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 dot. Means the training examples are column wise in column. See, maybe difficult to understand. Let's see. The final paper, the same type of question will be given in as assignment. I have no idea actually. Maybe like that. First time I'm teaching it. So, so you can understand this is phi transpose, okay, and phi will be transpose of that, okay. So this is the expression I've got. Means I have transposed. Means here phi was a vector, okay. I have transposed that to a matrix, and t was a scalar. I have made that a vector, okay. So like that, and that is due to the number of training examples I have got, okay. To remove this summation and make it a fully vectorized one, okay. Vectors and matrices. So now take transpose on both sides, okay. And I have written the RHS on LHS, okay. Then take phi transpose phi inverse on both sides, and you will get this expression. This is called Moore-Penrose pseudo-inverse or normal equation. It is called normal equation. So this is our what do I call mm, analytical value of W. Means we do not need to learn. As you know, there is an algorithm called gradient descent to calculate our best fit, but that is not analytical one. That is iterative method, okay. But this is analytical one. Using this expression, you can calculate value of W at one go. Means value of the parameters, okay. So this is the sixth question as well. Ninth question, okay. So as you can see, W is theta here. So x transpose x theta is equals to x transpose y. This is the answer, okay. Got it? Okay, x transpose x W is equals to x transpose y. Notations are different here. Let x be the okay. Any doubt? Yes, recording will provide, no problem. You can just unmute yourself and ask the doubt, no problem.
It's a great book to refer to understand this basic mathematics, like the mathematics calculations and all. I feel myself weak at it. So which book do I refer to learn so that it helps?
Okay. So see that there are three component methods which are important for machine learning. One is
Yes.
optimization, one is optimization, one is probability, and one is linear algebra. Linear algebra, you can use this lecture series. Just a second. You can use this lecture series for studying linear algebra.
Yes, sir.
You can use this lecture series.
Okay. Lecture series here. Okay. This is in
MIT college.
OCW.
Yes.
OCW. ocw.mit.edu. Sir, can you please put this link in the chat? Will this chat be accessible after?
No,
No, right?
you can just take it down, write it down.
OCW linear algebra from here. I'll just make a copy of it. Sir.
Probability. You put down probability. Bishop is only a summary actually, so maybe harder to learn.
Yes, sir.
The probability you can learn from IIT professor.
Hello, sir.
Yes.
Sir, that question number 9, can you please repeat again?
Miss, there's
That
nothing to repeat actually. You can see this expression is same as what I have told you. Same, right? Phi is x in the question, W is theta, and T is y. Okay, absolutely same, right?
sir, for that I'm asking the explanation, like how you'll get
As
that
I've gone through the full derivation,
answer.
I've explained it at every step. We've started from
So
the
that I
beginning.
could not able to understand. That's what I'm asking.
You can check the videos again. Okay, there's also reference in the Bishop. Okay, page 27, as I said.
Okay.
Okay, as
Sir, I missed on the.
Yes, sir.
there is in the Bishop as well. Maybe more explanatory as well. Maybe easier to understand. Okay, you can use this one
Okay, sir.
for reference. Yeah. Okay.
Sir, you said linear algebra to refer to ocw.mit.edu and probability in the IIT documents you said.
No,
And for the other
this is
one,
the
the
page.
last one?
This is the page. Maybe Professor S. Sarvaraj, 457. 457. For question number 4, I have done previously. Question number 4 and question number 5 is same. Okay, that 5 that previously I have done, same actually. Squared error, loss function, everything is same. Parameter, there were 3 parameters, it is 2, so it is even easier. Okay. Question number 3 is very easy. Just put the value of age, take the difference. Okay. Question number 2, as the correlation is 0, as you know, if correlation is 0 within two variables, that means that they are uncorrelated. Okay. That is why mostly does not explain why. Okay. Means, okay, they are not correlated. The regression line will not fit. Okay. The parameters can take any value here. Okay. 4, 5, 5, right? So then 7. Sure. 5 is actually a difficult one. Uh, so let's see. So there are k nearest neighbors, two query points due to linear regression fit. Okay, first you need find the k neighbors and then pass means a best fit through it through linear regression. So the data is locally linear. There is no consideration like that. Okay, and in non-linear data as well, linear lines can be fit. No problem with that. In order to perform well, this method would need dense distributed training data. Let's understand this. Any more doubt first of all? No. Okay. So dense is not important here. Okay. If it is sparse, that makes it easier actually. Uh, method has higher bias compared to KNN. Okay, okay, let's understand this. So, so in KNN, what we'll do is that we'll get the nearest points, and then for regression we'll take the mean, right? And and here what we will do is fit a straight line. Okay, not straight line, can be curve as well. Okay, and so the thing is, does it have a higher bias or not? Higher bias means underfit, right? So does it have a higher bias? Okay, let's try to understand. So let's see. So for that question means like we have got this nearest neighbors, and with KNN, suppose this is the answer, taking the mean, Motamoti central location, and for that other ones we fit a line, and for the x value try to predict the y value. Okay, let's see. Hmm. One case we are taking a mean, and another case we are acha acha acha. In the KNN case, that you can understand, we are biased using the mean. Actually, we are take understanding that this uh, mean is the only type of calculation through which we get to the best possible prediction. But in the this straight line fit, we are using parameters to adjust the line. Okay, so the straight line is much more flexible. Straight may be any curve. Okay, actually, so the KNN will have more bias actually. So KNN will have more bias. This is wrong. This method has higher variance. It's less bias, right? The KNN has more bias. Yes, this is the answer. Last one. Okay. Ridge and lasso is part of that using, you'll need to use prior with the likelihood, multiply both, and then maximize. From that we'll get the ridge regression, that is the square of the uh, means like W transpose W as the regularizer here. Okay, um, and in lasso there will W mod as the regularizer. So you have to understand, with our teach it next time, that as I said here, as I explained here, maximizing the likelihood, and suppose this phi x is this vector of phi x is very complicated, then it will try to fit it as good as possible, leading to overfitting. Okay, and for that we need to regularize. So that with the, as I have taught in bias and variance, the first method to get to the best fit is regularization, because most probably using powerful computers and powerful means a complicated phi will get to a overfit line, overfit curve. Okay, so we need to use regularizer to get to our best fit. Okay, so this question maybe you can leave or you can guess. Okay, uh, but I will derive next time. Okay. And question number 7, when only working on a small data set. Okay, so what happens in small data set, that as you have uh, so what happens if you have lot of data, then you'll generalize better, even with a complicated phi. Okay, so in small data set we should choose a simple model. Okay, so means that we have high bias. Okay, high bias. Okay, high bias. And a large data set you can take a low bias, no problem with that. Okay, because in low bias means like it has tendency towards overfitting, but as data is more, you'll have different more knowledge, you'll have get more knowledge through it, so the tendency of overfitting will be less. Okay, so this is it. And maybe you can do this no, this one is also not told you. Okay, but others you can do very easily. Okay, any doubt? Can you repeat 4? Let's see, 4 4 is actually 5 here. First assignment 5. Okay, here first assignment 5 is 4 and 5 are same. Okay, they are here 3 parameters, and in 4 there are 2 parameters, so easier actually. You can just use this expression to get the answer. Like maybe you can do it right now. You can use to calculate 4, you can use this expression that we have derived right now. Okay, maybe a good exercise to understand the expression as well. You can use this expression. Phi is uh, this one. Okay, so what it will be here, as you can see, phi will be here. Let me write. Phi will be here 1 and -1, and then 1 and 0, and then 1 and 1, and then 1 and 2, right? So this will be phi here. So phi, use phi this one. Okay, transpose everything you can do, inverse.
How you have written, sir, that 1 minus 1, 1, 0?
As you can see here, I have defined phi transpose there during derivation as 1 x1 1 x2 1. 1 is the uh, training. Okay, first example. Superscript is denotes the first training example. Okay, then second, then third, then fourth. So here we have to take transpose. Okay, this is phi transpose. Okay, this is phi. Okay, this is phi that, and t will be the vector of the y values. Okay, then multiply, you will get the answer like that. W will be like 2-dimensional, like that. This, okay, 2-dimensional vector. You can do it. Or maybe you cannot. You may not use the direct formula and can do by this way as well. Same thing. Okay, squared error, differentiate with respect to the 2 parameter a and b, and then solve. Okay, any more doubt? Any doubt? Question 3. Question 3 is easy. Just put the value of h Okay, equals to 4. Okay, whatever you'll get, subtract. So answer will be 15.2 into 4. What is that? 30.4, 60.8 is the answer. Okay, done now. Recording link I will share now. Okay. Okay, thank you very much, everyone. Link for optimization. Optimization. The best is this book. Okay. Maybe lecture series can be better, but I cannot remember now. Optimization. The best book is this word optimization. Just search. Just search here in Google. Optimization by Boyd. But you don't need to read the whole book because that much is not required. Just simple enough will be enough. Stephen Boyd is the professor. Okay, maybe you can use his lecture series, can be easier. Must be here somewhere. As you can see, YouTube only. Okay. Anything else? Okay, thank you very much, everyone. Link I will share. This recording is going on still. Okay. After that I will share. Acha,
Thank you, sir.
recording will be on YouTube. Okay. YouTube link I've told you. YouTube link is this one. YouTube link is this one. The recording will be on YouTube channel. Okay. Just note it down. Copy the link. Okay. I think everyone is done copying the link. Okay. Thank you.